Alright class, we're going to continue with the acceleration due to gravity equation and example problems dealing with it. So the example problem we are going to deal with is telling us the Sun has a mass of 330,000 times Earth's mass and a radius of 109 times Earth's radius. What is the acceleration due to gravity on the Sun, little g? This problem could be solved by simply taking Earth's mass in the last problem and multiplying it by 333,000 times Earth. But we're not going to do that. This problem wants us to do it another way. They say it's simpler. I don't agree that it's simpler. Just because you can do something another way doesn't make it simpler. But it is an important way that they want you to solve this problem, so let's take a look at it. They are going to compare the ratios using the equation little g equals big G times the mass over the distance squared. We can use that equation for the Sun and put that equation on top of that same equation for Earth. What's that going to look like? It's going to look like this. You've probably seen in one of your math classes simplifying two equations like this. Sometimes it's easy, sometimes it's not. Typically, when you're dealing with new variables that you're not used to, and you start to see all these letters and math with letters, that can be a little confusing. But hopefully, let's take a look and we'll figure it out. So, the acceleration due to gravity on the Sun is kind of like, hey, remember a person standing on a celestial body, particularly if it's a large celestial body compared to a small one. That person is going to have an acceleration due to gravity. That would also be applied to, say, a car or something like that on the Sun. Let's forget that it would melt. If you would call that melting. Maybe instantaneous liquefaction. I don't know. Anyway, so the acceleration due to gravity on the Sun is going to equal the gravitational force constant times the mass of the Sun, ms, over the distance between the two objects squared, where the distance between them in this case is going to be the radius of the circle of the Sun. So there's that equation, and they're saying, hey, what about Earth? Would have the acceleration due to gravity on Earth, which we already know is 9.8 meters per second squared, but that's also going to equal big G times the mass of Earth over the distance between something on Earth squared and that person. So we can just compare these two equations by drawing a line between them. And if we have any values that we can simplify, it might be easier than just going ahead and multiplying 333,000 times the mass of Earth to get the mass of the Sun and solve that problem that way. So instead what they're having you do is we're going to go ahead and rearrange these equations a little bit. We'll rearrange these equations a little bit. I'm going to come over here and write it in a way that shows the steps. So there's that part of the equation, and that's going to equal G ms over ds2. I haven't changed anything there, I just took it here. Now what I'm going to do different, here's a fraction and here's a fraction, and they're dividing them. So we're going to multiply those fractions. Remember, when you multiply a fraction that you were dividing, you multiply the reciprocal. Now notice what could cancel out if you do that. G cancels out on both sides of the equation, and what that's going to end up leaving you with is ms, the distance of Earth squared, over ds2 times the mass of Earth. And that's over here. So if I go ahead and put another equal sign to show how they got that, ms de squared, ms de squared over meds squared. So that's how they got to that step. A lot of times when you're given these example problems, you don't get to see how they make the leap from here to here, but that's what they did. They divided those fractions by multiplying the reciprocal. They canceled out g where they could. So now we have the force of the acceleration due to gravity on the sun divided by the acceleration due to gravity on Earth is equal to the mass of the sun times the distance between the Earth and an object on it squared over the mass of Earth times the distance of an object on the sun squared. Now, the next step is, remember that they gave us in the beginning of the example problem that the mass of the sun is 333,000 times the mass of Earth. So here is the mass of the sun, or here, and they're going to plug that in. So ms is 333,000 times me, the mass of Earth. So we're just going to plug that in for ms, and that's what they're doing here. Also, they told us in the example problem that the distance or radius of the sun, remember that we're talking about the distance between an object on the sun and the center of gravity of the sun, that distance happens to equal r, the radius. So we're plugging in the radius of the sun for d, but the radius of the sun, or distance of the center of gravity of it and an object standing on it, is 109 times the radius of Earth, or d of Earth. So for the radius of the sun, or diameter, or excuse me, not diameter, the distance between an object on it and its center of gravity is 109 times that of Earth. So they're just plugging that in right there. So where this ds squared is, they're plugging in 109 times the diameter of Earth. Now, once they do all that, is there anything else that can cancel? Well, yes, the diameter of Earth cancels on the numerator and denominator of that, and also the mass of the Earth cancels in the numerator and the denominator of that. Remember that they could have put parentheses there to show you that the mass of Earth is a value that could be canceled, because you were multiplying fractions, or factors in fractions. But anyway, therefore the gravity on the sun, the force of gravity, acceleration due to gravity on the sun, equals 28 times the acceleration due to gravity on Earth. It is 28 times 10 meters per second, or the 9.8 meters per second I'm making you use, or when you do that math, 280 times that. 280 meters per second squared, 28 times ours. So that's that example problem.